Welcome to Chapter 9 on Decision Trees. In this chapter, we explore one of the most intuitive models in machine learning, one that predicts by asking a chain of simple questions. Think about the last time you made a decision by asking yourself a series of yes or no questions. A decision tree works the same way, routing an observation through questions about its features. We will look at the anatomy of a tree, how it chooses where to split, why trees overfit so readily, and how pruning tames them. By the end of this chapter, you should be able to explain the basic idea of a decision tree and the roles of nodes, branches, and leaves, use trees for both classification and regression, and describe how a tree decides where to split, including the Gini index, entropy, and information gain. You should also be able to interpret a fitted tree and its feature importance scores with appropriate caution, train, visualize, and evaluate trees in Python, and apply a tree to a real consequential decision while reasoning honestly about its limits. This figure shows a three-level decision tree for loan screening. It tests four features in turn: credit score, income, debt-to-income ratio, and length of employment, with each internal node asking a single yes or no question. It gives us a concrete picture of how a tree routes an applicant to a decision. At its core, a decision tree makes predictions by following a sequence of rules learned from data. Trees feel so natural because they imitate the way people actually decide things. Before we go further, let us fix a few terms that describe the parts of a tree because the rest of the chapter leans on them. The root node is where the whole dataset enters and the first split happens. An internal node asks a question and splits the data on a feature. A branch is one answer leading to the next node. A leaf node holds a prediction, and depth is the number of splits along the longest path from root to leaf. In a classification tree, each leaf predicts a class. When the target is a category, the tree is a classifier. The engine driving a classification tree is the pursuit of purity, separating the classes as cleanly as it can. Trees handle numeric targets just as gracefully. Here, the logic shifts from purity to consistency, grouping observations whose values are close together. Building a tree is a process of repeated splitting. For a numeric feature, a candidate split is a threshold, such as age at most 35 or income above 50,000. For a categorical feature, a split asks whether the feature falls in a particular category. The Gini index is the most common way classification trees measure impurity, and it is the default in scikit-learn. For two classes, it equals 1 minus the sum of the squared proportions. A pure node gives a Gini of 0, while an even 50-50 split gives 0.5, the worst case for two classes. Entropy is a second impurity measure, built from the proportions and their logarithms. An even split gives an entropy of 1 bit, the maximum for two classes, while a pure node gives 0. This figure plots the Gini index and entropy against the class proportion in a two-class node. Both vanish when the node is pure and rise to a maximum at the evenly mixed point, where the classes are most jumbled together. Let us pin down the key idea. Impurity is a numeric measure of how mixed the classes are within a node. The Gini index and entropy are the two standard measures, both 0 for a pure node and growing as the classes mix. And trees grow by choosing splits that reduce impurity. So how does a tree decide a split is worth making? Information gain is the impurity before the split minus the weighted impurity after it. The weighting matters. Children are combined in proportion to how many examples each holds. So isolating a tiny pure group while leaving a large messy one does not count for much. These formulas are easy to state and easy to believe, but they only really land once you have used them to pick a split yourself. So let us imagine an online bookstore that wants to predict whether a visitor will make a purchase. We have 10 website visitors, 5 bought a book and 5 did not, and the tree must decide which feature to split on first at the root. We start with the impurity before any split. Of the 10 visitors, 5 bought and 5 did not. So the root node is as mixed as a two-class node can possibly be. Now consider a categorical split on whether the visitor is a returning customer. This divides the 10 into two groups of 5. Working through the Gini index, the impurity before the split is 0.5 and the weighted impurity after is 0.32. So, the information gained from splitting on returning customer is 0.18. If you prefer entropy, each child has an entropy of about 0.722, so the entropy-based gain comes out to roughly 0.278. Now look at a numeric split on minutes spent on the site. Because the feature is numeric, there is no single obvious split, so we have to search for a good threshold. We scan candidate thresholds for minutes on site, marking who bought and who did not. The threshold at 8.5 minutes turns out to give the largest information gain. Now lay the three candidate splits side by side, and the root split essentially chooses itself. Splitting on minutes on site above 8.5 gives a gain of 0.333. Returning customer gives 0.18, and whether the visitor came from an ad gives just 0.02. The greedy rule picks the largest gain, so the tree's very first question becomes, did the visitor spend more than 8.5 minutes on the site? That single split already isolates a pure group of buyers. This figure shows the information gained for each candidate split at the root. The tree greedily selects the highest bar, splitting first on whether the visitor spent more than 8.5 minutes on the site. Left unchecked, a tree would keep splitting until every leaf held a single training example. To stop this, we set rules: a maximum depth, a minimum number of samples to attempt a split, a minimum number in a leaf, a minimum impurity decrease, and of course, we stop once a node is already pure. These stopping rules are your main levers for controlling complexity, and they are the first line of defense against the overfitting we turn to next. The whole procedure, growing a tree by recursively splitting until a stopping rule fires, can be read as a single loop. This figure illustrates the recursive tree building algorithm. Data enters at the root, and at each node, the algorithm either makes a leaf if a stopping criterion is met, or picks the best impurity-reducing split and repeats the process on each child. Decision trees overfit more eagerly than almost any other simple model, and it is worth understanding why. The warning signs are familiar. Training accuracy far higher than test accuracy, a very deep tree, and many leaves that contain only a handful of observations. The cures all amount to forcing the tree to stay simpler, cap its depth, require more samples per leaf, prune it back, or set it aside in favor of an ensemble of trees. Pruning comes in two flavors. Pre-pruning stops the tree early during training using stopping rules, while post-pruning grows a large tree first and then trims branches that do not earn their keep on validation data. Pruning usually costs a little training accuracy, and that is the point. The pruned tree often does noticeably better on data it has never seen. One of the strongest selling points of a tree is interpretability. But interpretability has limits, and those limits depend on the particular fitted model, not just on the model type. Trees can also tell you which features mattered most through feature importance scores. These scores are genuinely useful for understanding a model, but they should be read with care. Pulling it together, decision trees offer a distinctive bundle of strengths. They are easy to understand and visualize, capture nonlinear relationships and interactions, need little or no feature scaling, unlike the nearest neighbor methods of Chapter 8, work for both classification and regression, and handle numeric and categorical variables with suitable preprocessing. They also have real weaknesses. They overfit easily without depth limits or pruning. They are unstable. A single tree is often less accurate than an ensemble. Large trees become hard to read, and greedy growth may miss the globally best tree. Those very weaknesses are what the ensemble methods of Chapter 10 are designed to fix. Here is the key point. Decision trees learn by greedily splitting on whichever feature and threshold most reduces impurity. They are interpretable, need no feature scaling, and handle both classification and regression. But their central weakness is overfitting. Depth limits, minimum sample rules, and pruning are the standard remedies, and a single tree is best seen as the building block for the ensembles in Chapter 10. Time for some Python practice. We will train a classifier on the Palmer penguin's dataset, predicting the species of a penguin from its body measurements. This code loads the penguin's data, drops rows with missing values, and picks 4 body measurements as the features and the species as the target. It then splits the data into training and test sets and trains a decision tree classifier, deliberately capped at a shallow depth to keep it readable. We cap the tree at a depth of 3, which both limits overfitting and keeps the model easy to read. A decision tree is one of the very few models you can literally draw. This short snippet uses scikit-learn's plotting helper to render the fitted tree as a diagram, showing each split and the structure of the whole model in a single figure. Each box in the drawing shows the splitting rule, the impurity, the number of samples that reach the node, and the predicted class, so you can trace exactly how a penguin is classified. Now we switch to regression. This code loads the California housing dataset, splits it, and trains a decision tree regressor capped at a depth of 5, then reports the error using mean absolute error, root mean squared error, and the R-squared score. For regression, each leaf simply predicts the average target value of the training districts that fall into it. Let us bring this to life with a case study. A community bank once helped screening loan applications, deciding whether to approve or reject. Because lending is regulated and applicants have a right to an explanation, the bank values a model whose reasoning it can clearly articulate. A decision tree is attractive here precisely because its logic is legible. Yet, interpretability does not excuse the bank from the hard work. The lesson generalizes. An interpretable model is a gift, but it does not remove the obligation to validate carefully, choose metrics thoughtfully, and use predictions responsibly. The following code synthesizes a small loan application dataset, trains a shallow decision tree, and then prints the learned rules in plain text so we can read them directly. This code generates synthetic applicants with income, credit score, and debt-to-income ratio, labels each as approved or rejected by a simple rule, and assembles them into a table ready for the tree to learn from. The printed rules expose exactly which thresholds the tree learned from the data, making it straightforward to audit whether they align with the lending criteria the bank intended to apply. To summarize the chapter, a decision tree predicts by asking a learned sequence of questions, routing each observation from the root down to a leaf that carries the answer. Its defining weakness is an eagerness to overfit, which depth limits, stopping rules, and pruning are designed to control. If you would like to go further, look into introductory treatments of decision trees and recursive partitioning, the scikit-learn documentation, material on cost complexity pruning, and applied case studies in credit scoring and medical diagnosis. That brings us to the end of Chapter 9 on decision trees. Next, we will see how combining many trees into ensembles overcomes the limits of a single one.